All right, hello everybody. It's great to see you all here. This conference is actually happening, which is a bit of a surprise, but it's wonderful. So thank you all for your talks and collaborations and discussions. Yes, I'm Scott. I'm a postdoc here at the Institute for Theory and Computation here at the CFA. And I'm going to talk a little bit more about high-velocity clouds. So I've been looking at the TNG50 simulations and trying to understand where some of these HVCs could have come from. Obviously, we just saw this wonderful image, so I'm not going to talk about it specifically, but the one thing that I want to talk about is where simulations come in. And the thing that simulations are really great at is time evolution. That's the one thing we're missing with our observations. We can see this one specific point in time with these beautiful H1 maps and the column density, or the absorption spectra that Andy talked about. But to see where things came from, where it's going, that's where I've been turning to simulations to see what we can learn. And so within TNG50, Annalisa and collaborators have put together a sample of Milky Way and M31-like galaxies. And so I looked for one of those. But beyond that, there's one additional component of the TNG public data release that made this analysis possible, and that's the sub-boxes. So in addition to the full volume with 100 snapshots, there's 3 sub-regions of this simulation with thousands of snapshots every 6 million years. Well, one snapshot every 6 million years that leads to thousands of snapshots. And so there's one of these Milky Way-like galaxies in this sub-box, in one of these sub-boxes, 537941 for anyone counting. And this is the one that we analyzed in this work to look for these high-velocity cloud analogs. So to do that, we recreated the Voronoi mesh around this galaxy out to 200 co-moving kiloparsecs. And we created a catalog of cold clouds, connected Voronoi cells that all have temperatures less than 10 to the 4.5 Kelvin. This technique, I believe, was originally used by Dylan in a paper back in 2020 looking at cold gas around luminous red galaxies, and then also by Rahul Ramesh last year looking at the Milky Way M31 sample at z equals 0. And then once we have this catalog of cold clouds around the galaxy, we compare their would-be observed line-of-sight velocity with the disk rotation. Just like Andy said, we isolate the high-velocity bits as the components that are moving fast relative to the disk rotation. And so any of these cold clouds that have more than 70 kilometers per second deviation from what we'd expect the disk to be doing, those are our high-velocity clouds. And so we end up with something that looks like this. Here's, in the background, there's a projection of all the gas, which, as people have been saying, the contrast is not great, so sorry. We have all of the gas in this galaxy, and the gray shaded regions are our HVCs. So we can see there's more of our HVCs in the southern hemisphere, which I'll talk about in a bit. But there's also a whole range in sizes. There's large ones here, there's smaller ones, filamentary ones, more blob-like ones. And they are relatively close to the disk. Andy was talking about some distances within about 10 kiloparsecs. Ours are a little bit further out, about 50 to 60 kiloparsecs away from the disk, with one weird guy way out here. But they are a little bit further out than perhaps the observed HVCs, and that's something that we're looking into now. But what does this look like from Earth, quote unquote? The left, I'm showing that same projection, the edge-on projection, just showing the high-velocity gas. This is the face-on projection. But here's our H1 column density map from Earth. And so these, we see some large structures here, like perhaps complex C, some smaller filamentary pieces, and some little dots probably at the resolution limit. But a whole range of different features. And then our circles, or our enclosed regions, are our detected cold clouds. And so this is plotting 2 different things. We're looking at the H1 column density, which is how HVCs were originally explored. And then these are cold clouds of connected Voronoi cells less than 10 to the 4.5 Kelvin. So they're not necessarily tracing the exact same thing, but we do see good overlap with some of these H1 structures and our identified cold clouds that is our HVC analog sample. There's some blobs along the center here, along the galactic plane, and these are the edges of the disk warp, and so those were excluded from our HVC analog sample, so that's not why they're outlined. And some of these smaller dots are are fewer than 10 cells, and so those are unresolved, and we didn't include them either. But then once we have this HVC analog sample, you do the same analysis on each snapshot, looking for these cold clouds, and we connect the dots. We look for where these HVCs could have come from by propagating the positions and the velocities of each cloud forward in time, and then looking for overlap with cold clouds that we detected at that next snapshot. And so we end up with merger trees for each of these HVCs. So here's our HVC analog at our final snapshot. And then here are all the cold clouds that made it, basically. And so we can trim the dead-end branches and smooth this out, and we get a continuous history for each of our HVC analogs. And so that looks something like this. Here is six different properties of one of these HVC analogs as a function of time. We have galactocentric radius, distance to the nearest detected subhalo, so looking if it's a part of a satellite or not, galactocentric radial velocity, circularity, which is the z component of the angular momentum divided by the total angular momentum. Z component is, or the z direction is aligned with the disk, so values of 1 are disky orbits. Basically, it's probably within the disk. And then its temperature and ratio of cooling time to freefall time. And so all throughout this history, we have a temperature below 10 to the 4.5 Kelvin because it's one of these cold clouds that we've been tracking all the way through. But we want to track beyond this cold cloud phase as well. And so we look at all of the particles that make up this cell at the earliest detected time, and we trace those gas cell particles back further. And we see that the temperature goes up. This is the mean value in black, and the values of each cell in blue. We see that the cells move further away from the galaxy, and the temperature goes up, the angular momentum does weird stuff. But based on the properties of, or based on specific values from these properties, we can catalog the origin of these HVCs. So we look at the initial radial position, separation from a satellite, and radial velocity. And we look at the maximum value of the circularity, the temperature, and the cooling time to freefall time ratio. So we have these 6 data points for every HVC. And based on the position of the HVC in this 6-dimensional space, we can say, well, where did it come from? And so here are 2 projections in this 6-dimensional space, looking at circularity versus initial radial position and radial velocity versus initial radial position. And things that originate in the disk should start near the disk, so small r0, and either positive radial velocities, they're outflowing, or high circularities, they're still in the disk moving around before they're thrown out. Of the remaining HVCs, those that are far away from the central galaxy, high R0, and small separation from a satellite, those came from within those satellite galaxies and then were stripped out and formed the HVCs later on. And all the remaining clouds we classify as forming from thermal instability, either out of the warm circumgalactic medium for clouds that maximum temperature doesn't reach half the virial temperature, and then from the hot phase of the CGM for hotter clouds. And so this is our distribution of clouds that we end up with. Most of the clouds form out of the thermal instability of the warm or the hot CGM, and then we get about an even split between the CGM, or from the satellites and from the disk. But if we look at the distribution by mass, the satellites dominate over the disk population, and that says that the HVCs we see from satellites are generally larger and generally more massive than those that are spat out from the disk, which makes sense. And so in my last 1 minute, the whole goal is to see if we can constrain the origins of our Milky Way HVCs. So what do these HVCs look like at the present day, or at the final snapshot, based on their origins? And so a few highlights here, since I'm running out of time. The metallicity distribution based on origin is down here in the bottom left. And most of the clouds are right around 0.1 solar. And that's due to the strong mixing as these clouds move through the CGM. They all end up sort of similar metallicities, with a few tails higher for the disk origin, and then this large tail lower for the satellite origin HVCs. And we believe that's because the satellites are more protected as they pass through the halo due to their dark matter component, and there's less mixing going on there. And then in terms of the radial velocities, we see a strong positive radial velocity distribution for our disk origin HVCs, which makes sense. Those are the ones that are coming out of the disk, moving in positive radial velocities. Everything else is inflowing, which is consistent with the data. Most of the HVCs are falling in. And with that, I'll leave up my summary plots. Thanks so much.
Very cool stuff, Scott. I love the way you did this novel analysis. When I look at what you've got and I compare it to what Andy and Jess said, and I think about what we also see in Foggy, which is very similar to this, clouds distributed after 40 kiloparsecs, I worry that we're failing the most basic test, which is that the clouds are in the wrong place.
Yeah.
So what do we do about that?
That's a fantastic question. And so I am thinking a lot about the feedback models that are implemented in these simulations. Because as you get closer to the disk, those models play a much larger role.
Yeah.
And we know they're not right. They'll never be perfect, but there's some improvements we can make there that may change what's happening in the disk-halo interface. And so that doesn't discount the fact that we have clouds here in the simulations and we don't have them in the Milky Way, or it seems like we don't have them in the Milky Way. That would merely add clouds closer.
Yeah.
And so there's still some discrepancies there, but that's how I'm thinking to approach this next.
Okay. I'm with you there.
Great. Sorry.
This is so cool, Scott. Thank you for this thought.
Thanks.
I'm curious whether you can resolve any potential evolutionary pathways between HVCs and IVCs, and whether they, like HVCs will eventually evolve into IVCs, whether they won't. Like,
Great.
can you actually resolve IVCs as well with this method? And like trace that forward in time.
That's a great point. Yeah, so I haven't split those out specifically, but we do have, we have the radial velocities at the present day, and we can just break them up into smaller subgroups and explore, and I haven't done that yet, but that would be an awesome thing to do. Yeah, thanks.
Sure. In some of the earlier talks, we heard that the medium around these HVCs is intrinsically multi-phase.
Yes.
And now that you've sort of identified these halos in the at least the coldest component in the simulations, have you looked at the temperature and density distributions in the sort of this interface region between the coldest part and the hot coronal TGM?
Yeah, I'm working on this now actually, and so I've been trying to make some mock absorption spectra through these HVCs to see like what's there. And we do see absorption in a lot of these higher ions, silicon-2, silicon-3, carbon-4, in the simulation at the same velocities as this H1 as well. And then there are also some, as you can see perhaps here, it's a little small, but there are a few of these outlines that don't have detectable H1 because they're further away. And so we see ionized gas with very low H1 column density. And so that would be an ionized HVC, which have been detected around the Milky Way as well. And so yeah, it seems to line up with the observations surprisingly well, and I'm working on finalizing this stuff too. Thanks.
I was just going to say, do you see any low metallicity outflow in clouds?
I haven't looked for that specifically, but I don't think so, because I think all of the outflowing clouds, so there's some here that are outflowing and from the thermal instability didn't come from the disk, and so there might be one or two, but I haven't picked those specifically. We should chat.
Exist in the data.
Yeah, which is extra mystery.
Yeah.
Awesome talk. It's interesting in the plot, in the scatter plot of angular momentum alignment versus just the angular momentum alignment. That regardless of the origin, they all correlate with the disk, right? All HVCs.
Except for these two.
Oh, okay.
But yes.
Yeah, I was wondering, are there like any trends based on origin, where for example, the ones that originate from satellites are less rotating?
Interesting. Yeah, I have a version of this plot that has all of the different origins for all of them, and we should look at that. I haven't looked into that too much, but yeah, there are some interesting things we could probably pull out of that. Thanks.
Great, it's time to move on. Thank you very much.
Thank you.